Let's now do a little bit of formalization of the things we've learned by looking at some of the properties of the Laplace transform. First of all, we generally represent the operation of taking a Laplace transform with a cursive L, as I've shown here. If we are taking the Laplace transform of any kind of a function of t, this could be our input signal or our output signal, the result of this is written as the capital letter as a function of s. Now I'm going to use this notation to show you some of the properties of the Laplace transform. These are rules that apply to taking the Laplace transform that will apply regardless of what the function is. Our first important property looks like this. The Laplace transform of any constant, here written as capital A, times a function is equal to that constant times the Laplace transform of the function. Let me show you an example of this property at work. Here I'm showing the Laplace transform table. From this table, we see that the Laplace transform of, we'll look at line 3 here, the Laplace transform of the variable t is 1 over s squared. I'll write that like this. The Laplace transform of t is equal to 1 over s squared. Now, let's suppose that we were trying to take the Laplace transform of, say, 5t. We can combine this property that we just learned together with the line 3 of our table to find the Laplace transform of 5t. By applying the property, we'll call this property number 1, to this problem, we can see that this is equal to 5 times the Laplace transform of t. And since the Laplace transform of t is 1 over s squared, this will then be equal to 5 over s squared. Let's take a look at another property. Property number 2 of the Laplace transform tells us what we do when we have the sum of functions. The Laplace transform of some function f1 of t plus or minus a second function f2 of t is equal to the Laplace transform of the first function plus or minus the Laplace transform of the second function. Let's take a look at an example of how we can apply this property, which we'll refer to as property number 2. Let's suppose that we want to take the Laplace transform of a sinusoidal function. Here, we're going to start by applying property number 2. Property number 2 tells us that the Laplace transform of this sum of functions is equal to the Laplace transform of the first function plus the Laplace transform of the second function. Next, we can apply property number 1 to pull out the constants in these two functions. Now, let's look at our Laplace transform table and see if we can find the Laplace transform for these two functions. We're going to look down the rows of this table until we find a function that matches the kind of function we're trying to take the Laplace transform of. Here we have sine omega t. In our Laplace transform table, any variable that is not t is a constant, and we can match that constant to the Laplace transform on the other side of the table. Sine omega t matches both of our functions where we have a constant plugged in for omega. So we're going to use this row of the table. In our first function, omega is equal to 10. And in the second function, omega is equal to 2. There are two more properties of the Laplace transform that will be particularly useful to us. So let's move on and take a look at properties number 3 and 4. Property number 3 of the Laplace transform tells us what we do in the case of having the derivative of a function. The Laplace transform of d by dt of any function f of t is equal to s times the Laplace transform of the function minus the value of the time function at 0. This is why in our Laplace transform examples that we did in the previous videos, we said that we were making the assumption that the initial conditions are 0. Anytime the initial conditions are all 0, the value of this term, f of 0, will be 0. And we'll be left just with this first term, s times f of s. We've already looked at several examples of applying this property. For example, when we were taking the Laplace transform of our signals, such as x dot of t, we have been writing this as s times capital X of s. The reason why we've been making this association is because of property 3 of the Laplace transform. In doing this Laplace transform, we've been assuming that the value of x at 0 is equal to 0. Property number 4 of the Laplace transform is very similar to property number 3. It tells us what we do in the case of a second derivative. The Laplace transform of a second derivative is equal to s squared times the Laplace transform of the function minus s times the value of the time function at 0 minus the value of the derivative of the time function at 0. Once again, we typically assume that the initial conditions are 0, so that these values go away, and we're simply left with s squared f of s. This is why we've been using the rule that anytime we take the Laplace transform of a derivative, we look at the order of the derivative, add that many number of s's, and then the Laplace transform of the function. In fact, there's a fourth Laplace transform rule that gives us the inverse of this idea. Rule number 4 tells us that the Laplace transform of the integral of a function is equal to the Laplace transform of that function divided by s plus the integral of the time function evaluated at 0 divided by s. Similarly to how we have assumed initial conditions to be 0 above, we often assume that the initial condition here is also 0. Thus, we're left with the general rule that the derivative of a function corresponds to multiplication by s in the Laplace transform domain, and that integration of a time function corresponds to multiplication by 1 over s, or division by s, in the Laplace transform domain. By applying these rules and using a Laplace transform table, we can find the Laplace transform of most, if not all, functions that we're likely to encounter in systems analysis.